Combination of capacitors, we have two types, that is the capacitors in series and capacitors in parallel. Once the source is on or the battery is on, there is flow of charges. Let the system of capacitors be replaced by a single equivalent capacitance. Hello everyone, I am Brinda, Faculty of Physics from Vidhyaashram Pre-University, College Mysuru, welcoming you all to Session 5 of Chapter 2, that is Electrostatic Potential and Capacitance. In today's concept, we are dealing with the capacitance, that is the last bit of the capacitors concept. So, today's class, we are dealing with combination of capacitors and energy which is stored in capacitor as well as the Van de Graaff generator. So here, combination of capacitors, we have two types, that is the capacitors in series and capacitors in parallel. That means there you have to connect many number of capacitors either in series or in parallel, and here we consider three capacitors with us and we connect three capacitors in series and three capacitors in parallel. Series means it is one after the other. So this is the representation of capacitors. So series means 1, second capacitor 2 and the third capacitor 3. So there are C1, C2 and C3 are the three capacitors which are connected in series combination. Next is parallel combination of capacitors. Parallel means one below the other or one beside the other. It is in that way. So parallel, I can just go with, this is the main connection, and parallel you have capacitor, one capacitor, the second one and the third capacitors. So three capacitors are here which are connected in parallel, C1, C2 and C3. So you have two set of combination. One is series combination, another one is parallel combination of capacitors. So now dealing with the first combination, that is capacitors in series. Combination of capacitors in series, that means consider the capacitor C1 connected to the second capacitor C2, which is connected to the third capacitor C3, which is having a potential difference within the capacitor called as V1. Here the potential difference is V2 and here the potential difference is V3. And the charge which is placed on the capacitor can be called as, here it is plus Q, on this plate it is minus Q, this plate plus Q, here minus Q, plus Q and minus Q. So this is the setup of the capacitors in series. And these capacitors lies between point A and point B. So consider this as point A and this as point B in the experimental setup, and the overall potential is given as V. This can be the total potential of this setup, that is an experimental setup. So now we have the potentials V1, V2, V3. So the total potential is given by V. Total potential across the series combination is given as V is equal to V1 plus V2 plus V3. And we know that capacitance C is equal to Q divided by V is the formula. So this is that we know that C is equal to Q by V. So when this is a case, you can just take it down as V is equal to Q divided by C. Here the charge is Q itself throughout. Only the variation you can see in V1, V2, V3 when it keeps on moving into C1, C2, C3. So C1, C2, C3 are the capacitors which is having certain capacitance and its potential difference is said to be V1, V2, V3. So you can just write this equation. Substitute for V, it is substitute for V in equation 1. So this is your equation 1. So you have got V is equal to, you're substituting for V1, V2, V3, it is Q divided by C1 plus Q divided by C2 plus Q divided by C3. This is how you substitute, and we have the total potential over here. So call this as equation 2. And now let the system of capacitors be replaced by a single equivalent capacitance. That is, capacitors in series is replaced by, that is equivalent. This symbol is equivalent connection is given. That is, you're connecting, point A is connected to a capacitor and here B. The whole set, that is series set, is connected in one single capacitor. That is, there is just a replacement for the combination, but the value is same. So here we have capacitors in series CS, and there is a charge plus Q and minus Q, and the voltage, that is the potential, is said to be V. Now we will have to take up the formula. That is, we know that V is equal to Q divided by CS by the above setup, that is experimental setup. Replace from series combination to one single capacitor. Okay, so now applying this in case of equation 2. So consider this as equation 3. Applying equation 3 in equation 2, you have Q divided by CS is equal to Q. You take common out from this. So it will be 1 divided by C1 plus 1 by C2 plus 1 by C3. So this is the equation over here. Now on cancelling Q and Q from your left hand side as well as right hand side, you are left out with 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is the combination of capacitors in series formula. This is very important formula that you will have to know. So what is the application of connecting the capacitors in series? It is that from a higher value of capacitance, remember, from a higher value of capacitance, we can obtain the lower value of effective capacitance. That is the application of combination of capacitors in series. Now let us move to combination of capacitors in parallel. That is, again, I have told you, there is a wire which is connected to the capacitor. So it is in parallel connection. All three are connected to one, and this is a single line which is passing. And the equivalent of this capacitor is replaced by a single capacitor. Okay, so now let us give the names. So here there is a charge Q which is flowing throughout. Okay, and this can be C1, this is called as C2, and this is called as C3. So the charges which is flowing over here will be called as Q1, Q2, Q3, and the potential which is flowing across will be just V. There is nothing called as V1, V2, V3. It is just V is the total potential which is flowing through C1, C2, C3 capacitors which is connected in parallel, wherein the charges are divided like Q1 amount of charge, Q2 amount of charge, and Q3 amount of charge. It's like flow of water in a pipe. So pipe flows like this, that is, the water in the pipe keeps on flowing until and unless it has got three more other connection. Once it has got the other connection, that is a junction, few of the water particles, water molecules moves in one pipe, the other pipe and the rest of the pipes. It's like that. It divides itself. Similar way, the charges also is getting divided as Q1, Q2 and Q3. So this is a parallel connection of capacitor, whereas its equivalent connection is given in that figure, which is called as parallel combination of capacitor, and it is nothing but Q, which is having a potential of V. So now, having this set of equation, we know that total charge Q on this combination is given as total charge Q is equal to Q1 plus Q2 plus Q3, because Q1, Q2, Q3 are the flow of charges here in this part, Q2, and here it is Q3. So we have Q is equal to C into V. This is, we know that Q is equal to C into V. So on substituting for Q on your right hand side, it is Q is equal to, Q1 is C1 because capacitor 1 which is having potential of V, plus C2 V plus C3 V. So V is common out, wherein I can take V out, and it is like C1 plus C2 plus C3. Okay, so now call it as equation 1. Now we will have to replace parallel combination of capacitor into a equivalent setup, that is in this form which is given over here, this part. Okay, so now again we know that Q is equal to, by looking at this, we know that by having the same concept, it is nothing but Q is equal to C and V. What is C over here? That is Cp, because it's a equivalent capacitance, okay, whichever we have replaced from the parallel capacitors into a single equivalent capacitance. So it is Cp, parallel combination of capacitors and the voltage, that is the potential over here. So Q is equal to Cp by V, Cp into V. So call this as equation 2. Now substituting 2 in 1, we have Cp into V, which is equal to V into C1 plus C2 plus C3. V and V gets cancelled, so we have parallel capacitance Cp is equal to C1 plus C2 plus C3. So this is the equation for combination of capacitors in parallel. And what is the application of this? It is the vice versa of the previous one. It is like you obtain higher level of capacitance by using the lower value of capacitance. So that is all about the combination of capacitors, one in series and one in parallel. The only basic thing what you have to know is how is the capacitors placed, that is how is the capacitors connected, as well as the formula of the capacitance, that you will have to know. If you know that, it is very easy for you to derive until the series combination of capacitor or else parallel combination of capacitors. Now moving on to energy stored in the capacitor. So energy stored in capacitor. So we know the connection of capacitor to be given as in this form, which is connected to a battery. So the longer end, lengthier end is called positive and smaller end is called as negative, and here it's a battery. This is the connection. The line shows, that is, represents the connection, wherein these two lines are of the same size. So this is called as capacitor, which is having a potential across it called as V. Okay. So now this is a basic experimental diagram, that is a circuit diagram. This is called as a circuit diagram, which is present over here for us to understand how the charges are flowing here. Suppose initially the charges are 0. That means initially we consider the complete circuit is uncharged. Okay. Now Suppose if there is a battery which is connected over here such that it is ready to get charged, that is, the circuit is ready to get charged. So let us just check how does the charging process takes place. Once the source is on or the battery is on, there is flow of charges. Okay, so when there is flow of charges, we make sure that one side of the capacitor is conducting plate is with the positive charge and other side of the capacitor's conducting plate is in the negative charge. So we have positive charge as well as negative charge in a capacitor. So once the charging takes place, the positive charges from the negative side, suppose if this is a positive side and this is a negative side, the positive charges from the negative end of the conductor is removed from this place and it is put to the positive charge against attraction, because positive charge and negative charge attracts, but we are working against attraction. That means we are bringing positive charge from this end to the other end of the conductor, that is capacitor's conductor. Okay, so secondly, the other thing what we are doing is, in the sense, we are removing positive charge from this place against attraction and getting here towards the positive plate of the conductor. That means we are acting against repulsion, because like charges repulse. Okay, so against attraction and against repulsion, we act against attraction and repulsion. That is the process of the charging over here. So in order to charge the capacitors, that means in order to get from 0 to certain charge, 0 to Q, certain work has to be done. And that work done in bringing the charge from 0 to Q is said to be W is equal to V into dQ. How did we get this equation? We know that since potential, that is electrostatic potential, means work done in bringing a unit positive charge from infinity to that point, right? So it is like W is equal to V into Q. So there is change in charge. That means it's getting charged, because of which we will replace the Q by dQ. And we also know that C is equal to Q divided by V. So it can be written as V is equal to Q divided by C. So W is equal to, it is Q divided by C into dQ. So now we need to know total amount of work involved in this circuit during charging. So in order to know the total work done, we have to integrate the equation. So on integrating, we have integration of W, that is total W is equal to integration of W, which means it is integral of Q divided by C into dQ. So Q has got its partner as dQ and C is said to be a constant. We'll just take the C as constant and we are taking it outside. So we have W is equal to 1 divided by C integral of Q into dQ. And this is from where to where? It is, you're doing the work, you just charge to Q. So it is from 0 to Q. It is 0 to Q. So we have W is equal to 1 by C. This Q can be called as Q square divided by 2 into 0 to Q. So we have 1 by C, and you can just write it as, in the sense, Q is the variable which is integrated. So after integrating, whichever variable is there, for that variable you will have to replace it by Q or any of the, either of the number which are in limits. So it is Q square divided by 2 minus 0 divided by 2. So this goes, so you are left out with W is equal to Q square divided by 2C. And we also know that Q is nothing but C into V. So Q is the charge, this is also charge, just it is that one is in caps and one is in small letter. So it is like C and V is substituted in the place of Q. So we have W is equal to C square V square because it is Q square divided by 2C. C gets cancelled with square. So we have W is equal to C into V square divided by 2. So, and we know that C also can be given as Q divided by V. So, W is equal to, so it can be written as, considering this as capital letter Q, Q divided by V into 2 into V square. V gets cancelled with V square. So, we have W is equal to Q into V divided by 2. So, or half QV. So, it is nothing but work done V is equal to the energy stored in the capacitor. So, energy stored in the capacitor, the storage of energy is nothing but potential energy, which can be given in terms of U is equal to half into Q into V. So, this is the energy which is said to be stored in the capacitor. So, it is very easy for you to understand. Firstly, draw the setup, that is experimental setup or a circuit diagram, and then step by step you can just go through, like you can understand its theory concept, like there is removal of positive charges towards the positive charge. That means removal of the positive charge against attraction, towards the positive charge we are going and fixing, that is against repulsion. If you just know that concept, and you have to know that the work done from where to where during charging from 0 to Q, because initially it is uncharged, and final case we are making it to charge from 0 to Q. That is why you just take the interval from 0 to Q. This is a concept of energy stored in the capacitor. Now moving on to Van de Graaff generator. So this image gives you the Van de Graaff generator setup, and it's very easy explanation on this. So this is a one, that is, this is an instrument which is used to accelerate the charged particles. So here this was named after by American physicist because he has designed this. The American physicist name is Robert J. Van de Graaff. So this is named as Van de Graaff generator. So this is capable of producing large static electric potential. Okay. So now let us just check out its principle. On what principle does this Van de Graaff generator works? The principle on which the Van de Graaff generator works is, this is a charged conductor and this is the uncharged hollow conductor. Okay. When the charged conductor is brought in contact by this brush, okay, when the charged conductor is brought in contact with the help internally with the help of a brush with the external hollow conductor, that is, when the charged conductor, small charged conductor is brought in contact internally with the external conductor, the charges which is present in the small conductor is transformed with the help of that connection here which is given, that is a brush kind of a structure. So here we have experimental setup is, here we have pulley kind of a thing which is given by a insulated material. Okay, it's a rubber-like material, and here you have two spheres, out of which here one sphere attains positive charges, and here you have got the brush. So how is the working of the Van de Graaff generator? It is, that is, the below sphere is connected to a external source. The charges, that is the external source which produces positive charges. The positive charges are supplied to this sphere through the help of this brush. As you on the source, the positive charges from the external source is moved on through the brush to this pulley kind of a structure, that is a rubber insulating material. So that the positive charges are carried when this turns, keeps on turning, this pulley keeps on turning over the sphere. So while moving, the positive charges through the brush is supplied to this pulley and it keeps moving from here, and here the conducting material is present. So the charges, that is positive charges, goes and falls into the conducting material, that is a sphere. And from that sphere, the brush which is touching the sphere takes all the charges towards the hollow cylinder, and it assembles, that is the positive charges assembles uniformly on the surface of the hollow sphere. So this is the Van de Graaff generator. So now this process happens continuously throughout, and the potential which is acquired by the hollow sphere, outer sphere, will be greater. It keeps on increasing until it becomes equal to the breakdown potential of the air, that is the atmosphere which is surrounding it, and it will ionize the air, because of which the charges leaks away from the Van de Graaff generator. So that is all about the Van de Graaff generator. It is just that one is you'll have to know how it is performed, why it is used, its application and its principle. That's all about this Van de Graaff generator. So I hope you're clear with the Van de Graaff generator concept. So in today's class, we have studied the combinations in capacitance, combination of capacitors in series, in parallel, and energy stored in capacitor, as well as the final concept for you to understand, that is Van de Graaff generator concept. So let us all meet in the next class by upcoming sessions with a new chapter. Until then, have a good day. Thank you.